industrial scale, so you have multiple over that. So you say maybe jump. So then you can estimate jump size. Right? So the jump size you will have. This is the true jump size if you really have jump at the tau L. So this is the true jump size. Now in the reality, because I don't observe my prior process, because prior process is always observed with microstructural noise. So this one I have to replace by average. This location I have to be replaced by my estimated location, and then this value I don't observe it. I have to average for the data above this time point to damp down the microstructural noise, and I also have to average for the data below this estimated jump location, and this also damp down the microstructural noise. And so at the end of the day, I got my estimate of this, which is really the average of data points at the location which I think is a microstructural noise. Okay, so with that, you could compute jump variation process, because now you're just averaging of these, the jump size, estimate jump size squares, so you got the jump variation estimate. And the nice thing of using this or those more formal things is that you're able to say some mathematical results. So mathematical result is basically as following. So if I take my interval delta n here small enough, so small that there will be no more than 2 jumps in the little neighborhood, and also large enough also small enough so that if I move a little bit away from that, the prior process hasn't changed very much, and this is due to the whole continuity of Brownian motion. So if I take delta n equal to root n, so I didn't move very much. This is exactly due to the half derivative of diffusion process. And then this allows me to average data in the order of 1 over n. Remember, I have frequency of 1 over n frequency, so they have n data points I'm averaging here. Then you could show that the difference between those two is n to 1/4. So in other words, the cumulative jump variations is estimated with the rate of n to 1/4. So this rate of convergence is usually much slower than in non-parametric regression situation. In non-parametric regression situation, that Wolfgang has done many work on this too. So the rate of convergence usually is much faster than n to 1/4. So this is because I have only half derivative. So in our case, we have only half derivative. So heuristically, what you can estimate for the diffusion process is the rate of convergence will be about 1/4. So this is the familiar rate of convergence people do in non-parametric usually see. Okay, so now let me talk about volatility estimator. So volatility estimator now is become simple since I'm able to get my NT process, because I'm able to detect where the location of jump and the number of jumps. So this would be my my jump process, and this is the jump size that I will have at up to time t. So you just adding all those together. Then your adjusted data will be just your observed data. With microstructural noise, and you subtract by your jumps. So at the end of the day, so this is really what we are calculating. So now you could also after you subtracting the jump out. So now I'm in the situation of Aisa, Halia, jump, and the Michelin. So there's no jump in my process. So therefore, I could define the average subsampling. The average subsampling realized volatility. That is again the same as what we said before. Partition interval into k sub intervals. We subsampling every k data points. I compute my adjusted realized volatility at this frequency. That is every k points I compute 1. Now I have k starting points, so I just averaging all those k starting points. So I got this. So this is average subsampling is computable. And so our accuracy of jump removal is rely on the theory of Isahaliya and Jump, then all we really need to do is to equate our theory with that. So suppose that, this is just a mathematical notation if you like. So the continuous part of my process is xc, so this is the continuous part of my process, the jump being removed, and plus the same microstructural noise. So let me denote my yc like this. This I call ideal data because this data you never observe. You never observe this ideal data because this ideal data compared with our really observed data, the difference is this, right? So if we go back again, this is our real data generation process. So your observed yt is equal to this plus epsilon t. So I never observe. So this is my price process, and my observed data is this xt plus microstructural noise. So therefore, this yc is never available to you. Okay, so this yc is never available to you, but this is ideal. It's available to me. Then I could apply just Isahaliya and Michelin and the John's methods. So because it's not available to me, now I try to see is this also give you idealized local. Idealized average subsampling realized volatility is the same as what we will apply if this data available to you. So we were able to show that based on our construct data, the jump removed data. So this is the jump removed that we apply k scale. ASRV. So we got this. This is something computable. This is something that I would like to compute if it's available. So we basically said that something computable and some ideal quantity that you would like to compute will have Razor convergence looks like this as n quarter. So as long as my subsample interval k is sufficiently large, then this one will be small. And so therefore the whole thing here we want n to 1/4. And n to 1/4 is shown to be the optimal rates available for estimating realized volatility. Remember n is very large here because it's high frequency data. So it's not bad. N to 1/4 is not really bad. So because of this, now if I apply two scales that I call a jump two-scale realized volatility, just adding a j to it, so it means that the two-scale realized volatility apply to the situation where data contain jumps. So now I could compute this, right? This is a jump removal process, and apply to two-scale realized volatility. So I got this. So with a star, all I mean is I apply wavelengths to detect where the jump is and then remove the jump. Then you could show just like apply our theorem here, saying that this is ideal data, Isahaliya and the Michelin would like to use, and this is the real data we have here. So since the error here is about n to 1/4, so certainly if I apply scale k at this level, 2/3 just like Isahaliya and Yassin and Pair did, then you could get n6 that your estimator would have radar convergence n6, and this is the asymptotic variance. So in conclusion, what we basically says here is jump, is a long term, and jump 2 times scale realized volatility behave as well as those from the ideal data. So and the one reason is what we shown here, that our jump remove data behave like ideal data with the error that actually indicate by here. Okay, so this would be a more robust version than 2 times scale realized volatility because whether it has a jump or no jump, it will apply, applicable to there. And now you could also apply, after you do jump removal, you could also apply the multi-scale realized volatility, which is really a linear combination of subsampling estimator at different scale, at different scale here. And the scale here we have to use here. I know there was some typo I corrected last night, so probably different from your notes. So the scale I apply here is very high. At root n, this is the integer value of root n, and then plus sum 1, 2, 3, 4 after that. So this is Km, and this is Am is the linear combination of subsampling procedure you have, and the particular ways you have to choose here in order to make the rate of convergence n to 1/4. So in other words, we could also show, because of this equivalent theorem that we show here, now if I apply Lanzhang's paper, I think published in Bernoulli, or to be published in Bernoulli, then I could also get my estimator to have rates of n1/4. So this is the multi-scale realized volatility estimator. Okay, so actually you could also apply directly the wave-based estimator. Now I know it has been taking a long time, and let me just skip this part a little bit, because otherwise there will be a lot of procedures. But basically saying that you don't really need to directly, get the data, remove the jumps, and then apply Ayesa-Halia and Miquelin's procedure. You could just compute your wave risk coefficients directly, and then you could just compute those directly in order to get the estimator. But let me not get to that. So let's just look at the numerical data. So in order to measure the performance, so let me look at the data which I do simulation of minute by minute over 24 hours. That is, I have 1444 data points, and I did 5,000 simulations. And because the drift played no roles anywhere in our estimation procedure or mathematical performance, I just set equal to 0. Remember, we only talk about daily data with minute by minute, so the drift doesn't play any significant roles. Oh, I make changes here, still making error last night. Okay. So this is the, so we assume that the stochastic volatility model, that volatility process itself is OU process. Okay, so here, I'm sorry, there's a parentheses here. Apparently I changed last night, but I didn't change it quite correctly. Okay, so there's a parentheses there. So I generate log volatility according to this OU process, or if you like, Wasychek model. In financial term, this is really a Wasychek model. Okay, so I generate this, and this WT is the one driven the price process. This one is the one that driven the stochastic volatility process. So this is the generation, and then we add in jumps, 1 jump or 3 jump uniformly on 0 and 1. So in other words, we are computing our performer estimator conditioning on I have 1 jump on the price process, and the conditioning on I have 3 jump on the price process. So I also do a little bit of ranging of my microstructural noise level from 0 to 1 in 1,000. Okay, so our estimating procedure so far I have said is a lot of procedure I have talked. So I use various realized volatility, which I didn't talk very careful, but basically for those people who know wave risk, you could do it using Dolbesch's wave risk of order 8. And I do a 2 times scale realized volatility with jump process. So I have, when I have say 2 scales, I use 5 and the scale equal to 15. Okay. So when I talk about multi-scale realized volatility, I added a J to it. So that I'm averaging over the subsampling. Every 5 data points, I sample 1. Every 6, I sample 1. Up to every 15, I sample 1. I do weighted average according to the weighting scheme given by Lanzhang here. Okay. So according to the weighting scheme given by Lanzhang here, everything is determined. It just looks ugly, but everything is determined there. Okay. So this is, and then of course I have the realized high power. So I could use original scale or subsampling, further subsampling scales, like different every 15 data point subsampling. And I could also apply realized volatility and realized by power volatility and 2-time scale directly applied to data without removal of the microstructural noise. So here is the result. So in the case of no jumps, and but there's microstructural noise. So this is this is our basic procedure, the dotted procedure here, and this is realized by power. By power volatility because of microstructural noise. So the lower frequency you sample, the quicker you are shooting to the roof. And this is a subsample every 5 minutes. So this the noise accumulating getting smaller. And if I do, let's say every 15 points, so of course this is more robust, but on the other hand doesn't estimate very well. So what I'm presenting here is mean square error of the mean square error of my estimate. So from here we can easily see that the realized by power estimator is not robust at all to microstructural noise. And this one is compare our wave risk estimator. Again, I'm plotting the same graph here on this picture here. Now here I'm computing is realized volatility without any, so it's with microstructural noise work certainly quite poorly. And this is 2-time scale with scale equal to 15, which is quite robust, but on the other hand, the noise level, it's quite robust against the noise level increases, but it's not also the best estimator. And this is at scale 5, so when at the scale 5, 2-time scale, and the difference between time scale 1 and time scale 5, so this is not as robust to the noise as 2-time scale 5. Okay, and this is the jump realized volatility and this is, we compare with wave risk estimator. So you can see that our estimate with 15 is very robust against the noise. And of course, this case, this estimator and this estimator are about the same because there's no jumps in the data. You can, and this is realized. This is the jump variation estimated by realized by power estimator. This is done by wave risk. So wave risk is much better because of microstructural noise here. Okay, just purely because of microstructural noise here. So just to remind you what we use to estimate the jump size. The jump size is estimated by realized by power is using this. Okay, so there's no microstructural noise here. Now let's see the jump. You are forecasting very well, very predictable. 1 and 3, right? So with jump, now it's the same picture, but with jump, this procedure, this realized by power certainly will increase a little bit, but it's still not increase very much because it still have robust procedure against jumps. But all those, work, Aisa Halia and Miklan's one perform quite poorly. Just, compare this picture. One jump alone will make a picture from here, mean square error, jump up all to here. And also quite different scale here. This is much smaller scale. This is much bigger scale here. So it's just one jump alone will make all of those procedure, work poorly with or without microstructural noise. Without microstructural noise, sigma equal to 0, they will work very poorly. Okay? And this is our, our procedure, which is an order of magnitude. If you compare, this is 0.005, this is 0.0. This is 10 times scale of this one. So it's work much better. And again, this is unfair comparison, but nevertheless, I'm just saying the realized by power without jump removal, so without taking microstructural noise, certainly work worse than microstructural noise. Now with three jumps, the story remained the same. Of course, just what may be different is probably the scale make it different. Okay, so now let me just apply these the two real data sets and then conclude with my talk so that people can ask a few questions. I know it's being highly technical, but on the other hand, it's also simple. So this is euro-dollar exchange on the first 7 months of 2004. So this is your observed euro-dollar exchange rates. Well, in 2004 US dollar, I think being able to do something back. Okay, so and this is our estimate of daily. I mean, I have how many days? For 7 months, maybe 150 days, trading days also. So, oh no, 100 is maybe 60 or something. So here is estimated number of jump every day. So it looks to me like, according to our various analysis, there's a lot of jump every day in the exchange rates. Some jump are small, some jump are large. Large one you can see it, I mean small one your eye cannot detect it. So it's range from 2 to 8 jumps. I mean maybe 1 to 8 jumps per day. So some days are very quiet. Many days are very quiet, right? Maybe have 1 jumps and of small size, but some days have like 8 jumps. Okay, so this is the, this is the volatility of jump size. I think what we're computing here. So this is the realized volatility. I mean, that is the integrated volatility of every day. So what I'm plotting here is integrated volatility every day, and what I plot here is the what I plot here is contribution due to jump variation. So in other words, I'm plotting here is these two quantity going back to here is this and this. Okay, so the first one, volatility, I plot is continuous power diffusion. The other I plot is this. Now I have 170 days, so I have a plot like a yeah, I mean like a bar chart, if you like. I mean like this. So from here we can see that a lot of days actually jump variation could be just as large as significant contribution to the total variations. Like for example, in this, and could even dominate its corresponding continuous part. Okay, and we apply the same thing to yen dollar, and well, yen dollar a little bit quieter. A little bit quieter, and the number of jumps not as much as euro dollar on that particular year, and the contribution due to jumps is a little bit less than contribution due to volatility. Comparing with the previous slides here, and so what we finally doing is this. Okay, so we are doing a thresholding. That is the amount so many we do the ratio between the diffusion part and the jump part. So jump part divided by diffusion part, or divided by the total, maybe divided by the total variation part here. Then we are putting 2 lines here. So this line is corresponding to jump variation contribute more than 20%, and the other is corresponding more than 10% for euro dollars, and this is for yen and dollars. And as we see for euro dollars, actually there are 41% of jump contribution that are non-negligible. That is, there are 41% of days that have jump contribution more than 10%. There are 24% of days that have jump contribution more than 20%. So if you look at here, and for yen dollar, those numbers are a little bit quieter, corresponding to 30 and 19% respectively. That is, the jump contribution more than 10% or 20% have 30% of the day or 19% of the day, according to our analysis. So now let me just quickly summarize what we have talked. It's a lot. So we basically say 2 time scale realized volatility and multiple time scale realized volatility are highly sensitive to jumps. If you have just adding a small jumps, it will not estimate your volatility correctly. Realized by power, estimator are insensitive to jump but sensitive to noise. So subsampling certainly is not the most favorable one that we like. We use is a linear combination of subsampling methods. So realized volatility certainly is sensitive to both jump and noise. Okay. So we propose various methods to separate jumps from diffusions, and our proposed method would be against jumps and diffusion and microstructural noise. I'm sorry, not diffusions. And it performs as well as if the jump were known to you. And with J infundoric, it's always a multi-scale. It's always more efficient than 2 scales, particularly in the case of high microstructural noise. In the case of low microstructural noise, 2 scale could work even better sometimes, depending on how you believe it. And with our separation, now if you like, you could model the realized volatility like this. I mean, this picture, this is a time series, right? So this every day you have realized volatility further by using, let's say, ARMA model or something like that. And you could estimate other data and so on. So let me say thank you. Mm-hmm.
I'm a bit worried about this assumption because particularly when we talk about jumps, and jump is often driven by some announcements, and this was Wolfgang already mentioned.
Mm-hmm.
And particularly around announcements, we really know that this assumption of IID noise is clearly violated. So this is also what we have shown in our study presented at the Humboldt-Universität conference, and we're looking, okay, what happens with noise around news announcements. And in the worst case, there could be also, in particular in these situations, could be even a correlation between the efficient price and the noise, because they receive quite fundamental movements on the market. So my question is whether you need this assumption of IID, or whether you could relax it maybe for at least conditional IID assumption, which also has been done in some recent papers in this literature. How you can handle this such a situation.
Okay, so so now I see the model. So any model, whichever you put down, is an idealization, right? So it's just how much idealization you want to put, right? Certainly, I mean, your model, more complex model, is one step closer to the reality. I mean, so if you're willing to assume, let's say, conditional IID, or let's say, a mixing process, the weak dependence, so it would be more, more realistic. So I think you are also hinting is that you probably prefer, say, conditioning on the jump location than the IID. Is that what you said? You want to?
Yeah, for instance, or at least conditional on the history market information set, something like that. I think that would be more realistic.
Right.
Yeah.
I think I know the key question is, can we handle that? So okay. So in the IID case, I could compute the noise. So if the correlation between those are highly, so if they are highly, how to say, they are, let's say the nearly data point has very high correlation, then the adjustment. The only thing is this formula may change a little bit. Let's see where the formula may change. This formula may change. So if they are, let's say, uncorrelated enough, that doesn't change this formula. The philosophies certainly continue to apply. It's just like whether this formula here will looks like this, or summation or something that relate to the correlation of your microstructural noise. So there were some extensions like what you say you have, and also that like Aisa, Halia, and John has for these like a stationary time series. Mixing the microstructural noise. So the theory getting a little bit complicated once you do that, right? And but all those are doable because it's not really a complicated, highly nonlinear procedure. It's really more or less a quadratic procedure. So all you need to figure out is the contribution due to noise terms. That would be more complicated than this, and then you need to estimate the correlation. But if you assume that they are wide enough, wide enough, not wide enough, then the contribution due to correlation of microstructural noise can be negligible, depending on how you model it. So this is another one area that actually probably maybe should study more carefully. At the end of the day, your assumption does have an impact on your estimate of theta. So in other words, the estimate of theta depends on your assumption. If you assume that no microstructural noise, then this guy will be just zero, right? So if you assume independent, I got this formula, you assume another kind of dependence, you have different adjustment coefficients here. So so some issue of this certainly need to be studied further. We actually, as I said, prove the concept. And for me, more importantly, is the next step. Once I separate jump, how I would use my jump to do something related to risk management. Now somebody else would say, once I got this theta, how would I use this to do my portfolio location? So different people looking at different kind of things. But then the second part I'm talking have little dependence on the assumption I use. Yeah.
When you showed this transparency on the first 7 months, so I thought that you want to tell us something fundamental on the next one, actually euro dollar first 7 months. That you want to tell us something fundamental about the first 7 months of the euro dollar. But then you said 2004. Now is this data from introducing the euro in 2002 or is it early 2004 data? Why does it say first 7 months?
Sorry for that. Okay. You know that we have a lot of things going on in the life. I certainly wish that I could go back to, at the beginning of euro-dollar exchange or this first 7 months. And that basically means that maybe I wrote paper in 2004 and the data available to me was first 7 months. So that's all. I'm sorry, no particular significance on those first 7 months.
Okay, so now I understand this because I thought that you only just said 2004.
Yeah. Sorry.
Suppose you show this to central bank.
Okay, so to my colleague.
Then you tell him, oh, I had this after the 60s day, I had this jump, and then again a high jump. What would he say? So what are the fundamental economic components?
What are
what are the news there? Why are the jumps there?
Oh yeah, that's very good question.
Just re-describe the data.
Yeah, if my colleague in the central bank give me an offer with 20 staff members, I will tell him something. If he asks me for free, why should I show him anything? I mean, if you ask me for free, say, okay, Zhenqi, explain to me this. I say, why? Why should I explain to this? I just say there's a lot of jump there. What is called a jump need people to study further. I mean, I not get hired by central bank to do that. Why I should do that? No, it's just a joke. This is just a joke. I'm just saying, okay, there's a statistical.
But this question is interesting. I think if you had an answer for that, it would give you a future income stream.
Oh yeah, sure. I mean, my problem is I have one man in Princeton. I mean, Ben Bernanke has 3,000 men in his central bank. Asked me to do a lot. Certainly, it's beyond my capacity. That's what I'm trying to say. Right. And
you look at deviation of this scale. So one scale changes point direction. So this problem is, it's of course a question how we select this scale optimally. And the second question is whether one can apply multi-scale change point detection, which is also just collect information from different scales.
Okay. Oh, do I recommend this? Okay. There are two things what we do here. So, I mean, really, from mathematical point of view, all what I really want is something like this. That is, you are estimating the number of jump correctly, and the location of jump is at the rate of, let's say, 1 over n rate, a little bit slower than 1 over n rate. Now, practical issue certainly has more than that. So what is this scale, what I'm chosen? The scale I'm chosen here is really the lower scale possible, so that, the lower scale possible so that the noise exceed, unfortunately there's no blackboard I can write here, but this is really is the jump to no jump ratio. Now I want, and the noise, I know what is the noise level, so I want jump to exceed this. So for theoretical reason, there's no, this will work. For practical reason, of course, I agree with you. You may be even going even one more scale, or looking in more scale, maybe enable you to detect a smaller size of jump, which is possible. We didn't do that. We were thinking there's not many scales here I can choose anyway. So because this is already very close to n. So remember, mathematically, there are not much level I can choose here. For simulated data, I think we are taking the largest n such that this equal to that. I think that's what we just take. This in practice, of course, you can multiply by 1,000. I understand what you're talking, but So there are issue of choice of scales here. So as I said, this procedure seems already complicated to many other people. I just make it as simplified as possible before you and I got killed.
Usually when we talk about jumps, we want to detect the frequency of jumps. Also the distribution of the jump sizes. Here, I think you just focus on the variation.
Okay, so so as I said, this is a good question. As I said, we really, this talk, we are really provide some raw material or first order approximation to many people who like to talk. After we separate, what should we do after? I didn't talk, right? So suppose I'm able to detect jump correctly as what I says here, then I have waiting time. So if you like, now you can model your waiting time. And somebody maybe want to say, I want to see the jump size, because that would be related to also risk management. So different people have different applications. Apparently, I haven't gone to the stage that you are asking. So you are asking that what is the distribution of waiting time, right? So if you're willing to assume that, let's say if you are willing to assume is a Poisson process with certain intensity, then actually the number of jump size that we have here, no, not this one, this here actually give you information. For example, average, if I take average of this, it's basically every number of arrival per day. So if you assume parametric form, then actually I do have answer to partial to your question. So if you assume that is a Poisson process with varying intensity function, then of course I need to do further, maybe based on the data I have here, or based on the intraday arrival time there, and to analyze further.
Any more questions?